Okay. Okay. So let us start our further discussion on logistic regression. So far in the previous lecture, what we discussed about logistic regression was we started our discussion on defining the model for logistic regression. Okay, we started our discussion at defining the model for logistic regression, which was h of x is equals to 1 upon 1 plus e raised to minus z. So in short, here z is a linear function which is of the form theta 0 plus theta 1 x1 plus theta 2 x2 plus so on up to theta n xn. Whatever number of features you have, that will be your z. And then later on, you are passing this z from through a sigmoid function, in order to get a probability, in order to get a output in the form of a probability value. So we also saw that h of x will always be the probability of the instance to be of to fall into the class 1 given certain features. Okay, given certain features. So for example, if h of x, if your output h of x is equals to 0.7, suppose you are trying to classify into tumor or non-tumor data set, okay? You are trying to classify your data set into tumor data set and non-tumor data set, and suppose tumor data set is of class 1 and this is of class 0. And if your output after passing your data through the model is h of x is equals to 0.7, then it is read as it is 0.7, that is 0.7 is the probability of that instance to fall to be of tumor class. Okay, probability of the instance to be of tumor class. Okay, that is what we saw so far. Also later on we discussed that MSC loss function cannot be used in the case of logistic regression. We studied why it cannot be used in the case of logistic regression. We defined a new loss function in the case of logistic regression, which is binary cross entropy loss, which is of the form j of theta is equals to minus of y, by ln y hat by I mean h of x plus 1 minus y into ln 1 minus y hat. Okay, this was your loss function that we defined in the previous lecture, right? All right. So now after this discussion, your main idea is to find a best fit line. Okay, best fit line that separates your data set. Okay, a line that separates your data set. So your linear separability, we already discussed that your data should be linearly separable in the case of whenever you want to apply logistic regression. And currently we are sufficing our discussion to binary logistic regression. Okay. So in this case, what we were trying to do in the case of linear regression, if you recall, what we were trying to do in the case of linear regression, we were utilizing an optimization algorithm called gradient descent to identify the value of parameter such that your loss is minimum. Okay, that is what we are trying to do in the case of linear regression. Yes, similarly in the case of logistic regression we will implement something similar. So in the case of logistic regression also we will use an optimization algorithm to update the values of your parameters. So first we'll take initial certain values, random values of this parameter, and then we'll use an optimization algorithm to update the value of parameter by calculating loss and using the gradient descent formula. So what was your gradient descent formula? New value is equals to old value minus alpha, which is your learning rate, into the slope value. Okay, that is what your gradient descent formula is, right? That is your new update formula. So what are we trying to do in this case is, so here first what we are doing, the first step that we will be doing in the case of logistic regression algorithm is we'll be having certain features x, we'll be having certain features x, we'll pass it through the model, start with the training of the model, start with the training process, that is passing through the model. So we'll be having some initial values of parameters, where parameters are theta 0 up to theta n. These are your parameter values, which will be having certain initial value. We'll be calculating z, which is theta 0 plus theta 1 x1 up to theta n xn. This is your z value. Then later on, we'll be passing this through a sigmoid function. To get some probability value. Okay, get a probability distribution value for this particular data set. Okay, later on, after doing this, after calculating the value of h of x, which is also y hat, you can also call this as y hat, we'll be calculating the loss. And later on, after calculation of the loss, we'll be calculating del j by del theta. Okay, this is the value of slope. If you recall, your gradient descent formula was something like this. Your new value is equals to old value minus alpha into del j by del theta, which is called the slope value. Okay, this is the slope value that we have. So we'll be calculating this and later on updating the values of parameters, and till we'll reach an optimal less loss. Okay, loss is very less. We'll be continuing with the calculation of updating the values of the parameters. Okay, so this process is clear. Yes or no? Everybody is clear with this process? Okay, now right now, okay, fine. So now in this case, we'll be first estimating what is the values of del j by del theta. What is the value of del j by del theta? In order to calculate the gradient descent, in order to obtain the gradient descent formula, we need to calculate del j by del theta. So in this case, what is del j by del theta? Will be something like this. Here, we need to do multiple chain rule will be implemented. So del j by del y hat to del y hat upon del z to del z upon del theta. Okay, something like this will be your formula. Yes or no? Are you getting this? Partial derivative chain rule. Is this clear or not? If you recall, your j is dependent. J actually changes based on y hat. Your y hat is changes based on z, and z is changed based on values of theta. Yes or no? If you recall, what is y hat? Y hat is equal to 1 upon 1 plus e raised to minus z. Y hat, by y hat, I mean h of x. Well, your j is your loss function, which is actually minus of y log y hat plus 1 minus y log 1 minus y hat. Right? And your z is theta 0 plus theta 1 x1 up to theta n xn. Yes or no? This is the what is j here? J is actually loss. J is the loss. Through j, I am meaning loss. Yes, Priyank? Okay. So now I'm giving you 5 minutes. To calculate the values of del j by del theta. So you already know what is the value of loss. You have the loss function value. You have the y hat value, which is 1 upon 1 plus e raised to minus z. And you have z value, which is theta 0 plus theta 1 x1 plus theta theta to x2 up to theta and xn, which can also be represented as theta transpose x. Okay, this can also be represented in the matrix form. It can also be represented as theta transpose x. So you have all the three values. Let me write the loss value as well. So that loss, which is j, is equals to minus of 1 y ln of y hat plus 1 minus y ln of 1 minus y hat. Okay, all these three values you have. Now, can you calculate what is del j by del theta, which is del j upon del y hat upon del z, and del z upon del theta. Okay, using chain rule. So right now, I'm giving you 5 minutes to calculate what will be the value of this. Try to calculate the value of this and let me know. Okay, is anyone ready with the calculation yet? Okay, Jenna. Fine. So actually, the final should be something like this: del j by del theta should be for entire training data set. Okay, for entire training data set, I am mentioning it should be something like y I hat minus y I into x I, sorry, into xi for entire training data set. Are you getting something like this, Daniel? Okay, fine. Okay, let me tell you as of now, I'll explain, go through this. So we already know that del j by del theta is equals to del j by del of y hat into del y hat upon del z and into del z upon del theta. So first of all, let us go with del z upon del theta. We already know what is z. Z is equal to theta transpose x. You can also say that after performing with the help of calculation, for example, in some of the calculation, if you see online also, they will do is they will represent this in vector form. In vector form, how will it be represented? A vector of theta into vector of x, something like this. Okay. So whenever you perform with respect to theta, okay. For example, let us say that del z upon del theta 1 will be equals to x1. Whenever so z is equals to theta 0 plus. Okay. Janil, you have shared your answer, I think. Yes, let me see. Okay, I think if you will try to simplify this, you will get appropriate result. I think you will, if you try to simplify this one, and I think you will get the appropriate result. Okay. See, del z upon del theta 1 will be x1. Similarly, because z equal to theta 0, theta 1 x1 plus theta 2 x2 and so on. Sorry. Theta 2 x2 and so on. So in short, we can say that del z upon del theta will be equals to x. Okay, will be equals to x, right? Now del y hat upon del z will be equals to 1 upon 1 plus e raised to minus z. We know that y hat is equals to 1 upon 1 plus e raised to minus z. And if we perform del y hat upon del z, it will be del upon del z upon 1 plus 1 e raised to minus z. Now if you consider this whole as x, and if you perform the calculation, you will get something like this, which will be y hat into 1 minus y hat. The overall calculation will be something like this. I'm not going into detail of this calculation. I'll leave that calculation up to you. You have to perform this on your own. So it will be something like this, 1 upon 1 plus e raised to minus z, and again you will perform the calculation. You know that how to work with the chain rule, right? So I'm leaving that part up to you. You try by yourself, and if you find any difficulty, you may later ask me, right? So del y hat upon del z will be y hat into 1 minus y hat, and finally del j upon del y hat, we know that what is the, it is y into log of y hat plus 1 minus y into log of 1 minus y hat. So already we know what is the differentiation of log. Log is 1 upon x. Log of x is 1 upon x. So it will be y upon y hat minus 1 minus y upon 1 minus y hat. Something like this will come up. So if you perform the product of all of this, so your final will be del j upon del theta will be something like y hat minus y into x. So for entire training data set, it will be del j upon del theta is equals to summation of I is equals to 1 to m y hat I minus yi into xi. And for example, for theta 0, xi will be equals to x1 will be equals to 1. Okay, that is clear. Okay, is everyone clear with this? Yes or no? Okay, fine. Those of you who are what about others? I think some of you might face difficulty in performing the differentiation. I think some of you who are from D2D may not find it easy to perform this differentiation, but try it on your own. So this should be your final output. Okay, I'll also share with you the PPT. So in the PPT, I'll share with you the entire calculation, so you will be able to understand. But for now, you have to understand this is the calculation that will be performed. So you can see some of the basic differentiation formula, that what is the differentiation of log of x and what is the chain rule and all of this. So it will be helpful for you to understand this particular differentiation. Okay. So this is your final calculation. So your final gradient formula, your slope formula will be something like this. And your final gradient descent update formula will be nu is equals to old minus alpha, that is learning rate, into del j by del theta. So it will be theta, as for example, theta j, you will be iterating, continuously performing the iteration for theta j is equals to theta j, that is old theta j, minus sigma I is equals to 1 to m y hat minus y into xi. Okay, that is what you will be performing. Okay, this is clear to everyone? Yes or no? This update formula is clear to everyone? Yes or no? Okay, fine. So now, you can see that this formula that we have derived is similar to what we did in the case of linear regression. Yes or no? This is very similar. This is approximately same formula that we are getting in the case of linear regression that we are getting in the case of logistic regression. But the only difference in this case will be h of x, which is hypothesis function that we'll be using in the case of logistic regression, which will be 1 upon 1 plus e raised to minus z. That is the hypothesis function that we'll be utilizing in the case of logistic regression. That you have to remember, right? So up to this, everyone is clear? Any doubt in whatever we discussed so far in for the case of gradient descent formula in the case of logistic regression? Any doubt? Please feel free to discuss. You can unmute yourself and ask the question, or you may ask in the chat box itself. Okay. So also in the case of my portion for mid-semester exam, for your sectional exam, we'll be keeping up to, after this, one more topic that we'll be discussing is perceptron. We'll be talking about perceptron, which we'll talk in the next lecture maybe. So up to that will be there in from my portion in sessional exam. So from sir's portion, sir might already have discussed with you what will be there. So from my portion, this up to this will be there in the session. Okay, please keep that in mind, right? Okay. So everyone is clear up to this? Shall we proceed? Okay, fine. So in the case of linear regression, we discussed, if you recall, we had discussed something called regularization. What was the idea behind regularization? Anyone please mention what was the idea behind regularization? Why were we using the regularization in the case of linear regression? And what was the idea? What was it trying to do? Yes, reduce overfitting and remove complex hypotheses, right? That is what the idea was behind regularization. What was it trying to do? Regularization is mainly that is used in the case of overfitting. Whenever your model is overfitting on your data set, you will be using regularization to create and simplified hypothesis. Okay, your hypothesis function to be more simplified, that is why you are using, and regularization to penalize your values of parameter, to reduce the values of parameter. Yes, penalty to higher degree weights. So that is, for example, theta 0, theta 1, theta 2, and theta 3. Suppose all these parameters are there. So what you will be doing, you will be trying to reduce the values of parameters as much as possible so that your model is more simplified. Okay, more simplified model you are getting. So for example, if your data set is something like this is your model, this is your data that you have. These are your positive, negative samples, and suppose these are your positive samples. Okay, something like this. Okay, a good hypothesis function will be something like this. It's something like this. Your decision boundary will be created. But for example, if your model is trying to overfit, what it will try to do? It will try to create some complex hypothesis function. Complex hypothesis function, complex decision boundary it will try to create. In order to avoid that, we'll be utilizing regularization. So the concept is same that we discussed in the case of linear regression also. We discussed the regularization in detail. We discussed two forms of regularization, if you recall, ridge and lasso. Okay, two forms of regularization that we discussed was ridge and lasso. In the case of ridge regularization, what were we adding? We were adding a regularization term along with the square of the parameters. Yes or no? In the loss function. This we were adding in the case of loss function so that we are trying to minimize the loss. So we'll be also minimizing the values of parameter. But in case of lasso, we were adding lambda, that is regularization term, plus absolute values of your parameter. Absolute values of your parameter that we were adding in the case of lasso regularization. And also two of the things that we discussed in the case of ridge and lasso, that ridge regularization will try to minimize your values of parameter, but it will never be equals to 0. But in the case of lasso, yes, right. Theta will not be equals to 0. But in case of lasso regularization, your theta value can equate to 0. That is, lasso regularization will be used for feature selection. Yes. These 2 points that we had already discussed in the case of linear regression. So the implementation in the case of logistic regression is similar. Okay, in the case of logistic regression is similar. So your updated loss function for logistic regression will be j is equals to minus of y into log of y hat plus 1 minus y log of 1 minus y hat plus lambda into your your parameter square, lambda into parameter square. So your updated gradient descent formula will be you will be reducing this value. So it will be addition of this. So it will be theta j minus alpha into summation of I is equals to 1 to m y hat minus y xi plus lambda into theta j. Okay, that is what we are trying to do. Yes or no? Is it theta I? Sorry, not theta j. It will be theta I because we are summing over entire training samples. Okay, up to this, everyone is clear? Yes or no? This point is clear to everyone? Yes, right. All right. So this ends our discussion with the case of binary logistic regression. Now we'll start our discussion on multi-class, multinomial logistic regression. So far we discussed, whatever we discussed so far was with the case of binary logistic regression. Binary logistic regression will contain two target values, that is 0 or 1. Okay, only two classes were present, 0 or 1. But what happens in the case of multinomial logistic regression? What is the idea behind multinomial logistic regression? In that case, you will be having multiple classes. Multiple classes will be there in the output. So your multiple classes will be 0, 1, 2. So cat, dog, and some other horse. Okay, these are the three classes that you might have, or more than three classes will be there to classify your data set. in that case, your hypothesis function will also be changed, and your loss function will also be changed. Okay. You can also say that binary logistic regression is in a subset of this software. This multinomial logistic regression is also known as softmax regression. Multinomial logistic regression, other name of multinomial logistic regression, is also known as softmax regression, and it is a subset of the softmax regression. So you will be getting some generalized formula for softmax regression. So whenever you are trying to implement this in the scikit-learn library as well, if number of classes equals to 2, automatically it will be converted in the form of binary logistic regression. Otherwise, softmax regression will be applied in order to perform the classification. Okay. So now we'll see what is the hypothesis function with the case of softmax regression and what is the loss function in the case of softmax regression. These two things we'll be studying right now. So in the case whenever you have multi-class classification, whenever your data set has multiple classes, you will be applying softmax regression. Okay, that is what you will be applying. So your hypothesis function will be updated to something like this: e raised to zi upon summation of I is equals to 1 to C, where C is the number of classes. C is the number of classes. E raised to number of classes. E raised to, I think, yes, Zi. Okay, that is what here for a particular class. For a particular class. Okay, let me explain this. I'll explain this one so that you will get an idea. So if you recall, we were performing one-hot encoding. Do you recall one-hot encoding? What was one-hot encoding? Label encoding. You have studied about one-hot encoding in the label encoding section. Wherever, suppose you have a data set x1, x2, and your dummies, you are trying to create dummy columns. That is what you are trying to create. For example, x1, x2, you have a certain data set. Suppose three instances you have. You have 3 instances, and you are trying to classify your data set into 3 classes, 1, 2, and 3. These are the 3 classes that you have. So in the case of whenever you are trying to do this, in the case of your scikit-learn library, what it will try to do, it will create 3 different columns, and it will, for example, wherever the class 1 is there, it will keep it as 1, and rest of them it will be converted to 0. Similarly, 0, 1, 0, and 0, 0, 1. Something like this will be created. So similarly, what we'll be trying to do in the case of softmax regression. So softmax regression, instead of applying a sigmoid function, whenever you have a binary classification, you will be applying a sigmoid function. But whenever you have a multi-class classification, you will be applying softmax regression function. So what we'll be trying to do, we'll be getting an output something like this. Your y hat will have 3 outputs. You'll be getting a probability value for all the 3 classes, and some of the property that it should follow is all these values should fall between 0 and 1, and the summation of all these values should be equals to 1. So you can automatically see. So for example, suppose you are trying to classify your data cat, dog, and horse. Okay, these are the 3 classes you are trying to classify. Suppose this is 1, 2, and 3. So you'll be getting a y hat value. Y hat is actually hypothesis value. You'll be getting a hypothesis value for all these 3 classes. For example, 0.75, 0.15, and 0.20. I'm just taking an assumption. Okay, I'm just taking an assumption. So this will be your output value. So the property that it should follow is it should always be between 0 and 1, and the summation of all these 3 hypothesis values should be equals to 1, which we can already define. So for example, your hypothesis function that you have seen in the case of softmax regression is equals to e raised to zi upon summation of I is equals to 1 to c e raised to zi. Okay. So for example, for first class, for example, for cat class, your hypothesis function output will be e raised to z1 upon summation of e raised to z1 plus e raised to z2 plus e raised to z3. Why up to z3? Because we have 3 classes here: cat, dog, and horse. Okay, that is what we are trying to do. Similarly, for suppose dog, you are trying to perform what is the hypothesis value? E raised to z2 upon e raised to z1 plus e raised to z2 plus e raised to z3. And similarly for horse. Are you getting? So these 3 values you will be getting in the output in the case of softmax regression. You will be getting the probability values for all the 3 classes in your output whenever you are trying to perform multi-class classification. Are you getting this? What we are trying to do in the case of softmax regression, what is the hypothesis function? Yes, I am coming to this. What is Z? So Z is actually if you recall, in the case of sigmoid function, what was z? Z was theta 0 plus theta 1 x1 plus theta 2 x2. That was your z. Similarly, here also we have z1, z2, and z3, which is actually your summation of all the parameters, weighted summation of all the parameters. That is what all the features. Sorry, weighted sum of all the features will be your z. Are you getting? Yes, Ronak. Yes. So, any doubt up to this? Yes or no? Any doubt up to this? Okay, I'll repeat. So, okay, in the case up to binary classification, what we were trying to do in our hypothesis function output was 1 upon 1 plus e raised to minus z. This was your hypothesis function in the case of binary logistic regression. But now we are talking about multi-class logistic regression, logistic, that is multinomial logistic regression. In that case, what we'll be applying? We'll be applying a sigmoid instead of sigmoid function on your z. Instead of applying a sigmoid function on your z, that is your linear output that you are getting after performing the weighted sum, we'll be applying a softmax function. We'll be applying a softmax function on our z value. What is softmax function? Softmax function is this. This is your softmax function in the case of multinomial logistic regression, where you are trying to h of x will be equals to e raised to zi upon e raised to zi, summation of I is equals to 1 to c. For all the classes, you will be calculating the e raised to zi, and that value will be your softmax hypothesis. Okay, softmax hypothesis that you will be getting. So in the output, previously in the case of binary logistic regression, we were getting only one output, that is h of x is equal to 0.7. Suppose you are getting 0.7 as an output, then you were estimating that the probability of the instance to fall in the tumor class is 0.7. Okay, that is what we were estimating in the case of binary logistic regression. But here, since we have multi-class logistic regression, okay, multinomial logistic regression we are having, we'll be getting in the output, we'll be getting three values. For example, if you are trying to classify into three different classes, then you will be getting a y hat value for first, for second class, for third class. Okay, and it should follow two properties. That is, it should fall between, all the values should fall between 0 and 1. And the second property should be the sum of all these probability values should be equals to 1. Okay. Okay. We'll be taking different hypotheses for each feature. No. No. We'll not be taking, that is actually what will be happening. We'll be taking different hypothesis value for each classes. If you see, we'll be taking different hypothesis values for each classes. What is C? C is the number of classes. Okay. Okay. Yes. Up to this, everyone is clear? What is happening in this case? Right? So, Priyank, is your doubt clear now? Okay. So, your softmax hypothesis function is h of x is equals to e raised to zi upon summation of I is equals to 1 to c, where c is the number of classes, e raised to zi. So, you can see something like this. Your data set will be updated something like this. If you see, what will be your data set? You have x1, x2, and you have y, which is 1, 2, and 3. And suppose you have x1.7, whatever values you have, some random values you are having. Right now, I am considering 3 instances here. I'm considering 3 instances. And your y, suppose you have 3 classes. So you will be getting 3 y's in the output. y1, y2, and y3. Right? So we'll be getting 1, 0, 0, 0, 1, sorry, 0, 1, 0, and 0, 0, 1. So for each classes, if you see, technically, if you want to understand this through theoretical purpose, what will be happening is, in this case, we'll be creating Z1, we'll be calculating Z1, we'll be calculating Z2, and we'll be calculating Z3. So for Z1, for what will be Z1? Z1 will be all those classes. For example, you are trying to classify into dog, cat, and horse. Okay, you are trying to perform the calculation in classification in 3 classes. So Z1 will be all those classes, which is all those data set, where you are trying to classify into either dog or then either it is dog or it is some other class, dog or horse. Okay, it is actually converting into binary classification. If you see, yes, right. Could you please write the Z1? Yes. Okay. I'll come to that one. Wait a minute. Let me just clear this part. I'll come to that. Okay. Okay, so you can say Z1 will be all those data set where you are trying to classify into doc, either it is doc or it is in some other class. And Z2 will be all those data set which will be either into it will be either into cat or some other class. Similarly for Z3, are you getting this? So which this will be your this will how your data set, your training your model will take your data set. This is how your model will take your data set. So you can say, um, so you can say how many parameters we'll be having. So for example, here we'll be having 9 parameters. In this case, we are having 3 instances. So we'll be having 9 parameters. How will be having 9 parameters? For example, Z1 will be something like this. Wait a minute. So since we are having, just a minute. Okay. So for instance, 1. For instance, 1. For instance 1 will be calculating Z1, will be calculating Z2, and will be calculating Z3, which will be actually your, for example, your just consider X1, X2, and we have something like this. We have a Y output. Okay, we have a Y output. Fine. So what we are trying to estimate is, suppose 7 and 70. These are the two values that we are having in the first instance. In the first instance, these are the two values that we are having. And Y we are having Y1, Y2, and Y3. Here it is 1, here it is 0, 0. Okay, right? This is your this is how your output is. So in this place, if you go for a generalized Z equation, it will be something like this: theta 0 plus theta 1 x1 plus theta 2 x2. Okay, yes or no? This is what your output will be. But so what we are trying to do is, so your output will be something like this. Your parameter will be 7 into W1 into 0. W is wait for class 1. Wait for class 1. Since we are trying to classify into class 1, we'll be estimating for class 1 plus W0 plus 70 into W2 into class sorry. No, wait a minute. I'm just confused a little bit. 2 minutes. Just wait for 2 minutes. Okay, understand it like this. What I'm trying to say is, understand it like this. What we are trying to do here is, we are trying to classify, calculate Z1, Z2, Z3. For each classes, we will be trying to classify this. We'll be trying to calculate this. And then what we'll be doing, your softmax function will be something like this. For example, for first class, it will be Z1 upon Z1 plus Z2 plus Z3. Sorry, e raised to Z1 plus Z2 plus Z3. And similarly, for all the classes, we'll be doing something like this. So in each case, we'll be calculating Z1, Z2, and Z3. What will be for Z1 will be all the classes for which are in 1 or something else or some other classes. Similarly, the second will be in second class or some other class. And in the third, it will be third class or some other class. That is what we are trying to do. So you can say that your Z value that you'll be calculating will be based on those weights. You'll be updating those weights. Your for each classes, for each, you can also consider this something like you are for each Z1, you are taking a different logistic regression model. This is different model, this is different model, and this is different model. Just for assumption, I'm trying to say. So for Z, what we are trying to do, will be updating certain other values of parameter. You will be having, so for example, if you see for Z1, what we are trying to do, it will be having all those data set where your class is either one or some other class. Similarly for Z2, you will be having all those data sets where your class will be second or some other class. And similarly Z3 will be all those data set which class will be 3 or some other class. Yes or no? Up to this, everyone is clear? Yes or no? The division that I did here, that is clear to everyone or not? Yes. What about others? Everyone is clear up to this? So for each Z1, you can consider, for each Z1 will be having unique parameters. Will be having unique parameters or not? For each Z1. For example, for this Z1 will be having unique W0, W1 and W2. Similarly, for this Z will be having unique parameters W1, W2 and W0, W1, W1 and W2. So where, sorry, W is actually, I mentioned, I'm talking about theta only. So for example, Z1, Z2 and Z3, where 1 or some other class, 2 or some other class, and 3 or some other class, will be having unique values of theta 1, theta 0 and theta 2. Similarly, for this, we'll be having unique values of theta. And for this also, we'll be having unique values of theta. Yes or no? Since the data set here will be differing. Are you getting this point? Yes or no? Yes? Is everyone clear with this point? Yes or no? Right? So for each Z will be calculating, will be for each values of Z will be calculating hypothesis. So hypothesis value of e raised to Z1 upon sigma I is equals to 1 to C e raised to Z. E raised to Zi. Sorry, Zi. Let us take Zi. Okay? So that is what we are trying to do. The ultimate calculation for Z is actually theta 0 plus theta 1 x1 plus theta 2 x2. For example, we have two features here. So this is the generalized equation that we have. But for each case for Z1, Z2 and Z3, we'll be having unique values of, for Z1, we'll be having theta 0 for class 1. Let us take for class 1. For theta 1 for class 1, x1, and theta 2 for class 1, x2. Right? Similarly, for Z2, we'll be considering theta 0 for class 2 plus theta 1 for class 2 x1 plus theta 2 for class 2 x2. Are you getting this point? Yes or no? And similarly for Z3. And then we'll be estimating the hypothesis function for all these Z values, and that will be your output. So for example, if you are performing 4-class classification, you will be having 4 hypothesis value in the output, and the total of these values should be equals to 1, and each value should be between 0 and 1. Are you getting this? Now is it clear? Anybody is having any doubt? Hello? Okay, hello? Yes, please acknowledge whether there is any doubt or not. Can you please solve one example with data set? Okay. Wait. So just take an example. For example, x1, x2. There is y. There is y1, y2, and y3. Okay. Suppose x1 we have x11, x12, x21, x22, x31, x32. Okay. And we are trying to classify into 3 classes, 1, 2, and 3. So here, what will be the for the case of dummies that we are creating? The dummies that we are creating here will be something like this: 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, this is what your data set will be of the form. Now, for example, in Z1, we'll be considering for all the classes. We'll be taking Y1 in the output. So Y1 will be taken in the output for the case of Z1. So we'll be considering all those classes where there is 1 as an output and 0, 1 and 0. But in short, what is it? It is actually considering all these classes where the class label is actually 1 or any other label. In short, it is converting into binary form.
So it is actually taking a 1, wherever the class label is actually 1, there the output is equals to 1, and rest of the classes it is considering as 0 class, right? Similarly, Z2 will be all those classes where the class label is 2, or any other label. These are the two classes in which it will be dividing. That's why here the output in this 1 and rest of the classes are assigned 0. So all those values will be taken in Z2. Similarly, Z3 will be all those classes where we are considering for class label is actually 3 in the output and rest of the class. Okay, so we can write your Z equation. You can write your Z equation into something like this. For example, Z1 will contain overall Z equation will be theta 0 plus theta 1 x1 plus theta 2 x2. But for each Z, we'll be having different parameters. We'll be estimating different parameters. Yes or no? Since these are actually you are actually estimating different y's for each of the particular classes. You are estimating different y's. That's why you will be having different parameters values in each z, each of the z1. So your zi, so z1 will be equals to, you can say w0 let us stick with theta. So theta 0, for example, first class, you are trying to classify into class 1. Theta 0, theta 1, 1, x1 plus theta 2, 1, x2. Okay, something like this will be your in the Z1 output. Okay, so you will be estimating for class, it is actually, what is the output in this case? It is actually the output whether it is getting classified into class 1 or any other classes. Okay, so your output will be for Z1. Similarly for Z2. So Z2 will be having different parameters. Why will be having different parameters? Because we are considering this y, y2 in that case. Okay, we are considering different y, that is y2 in that case. That's why it will be theta 0 for class 2, theta 0 for class 2, theta 1 plus theta 2 into x2, x1. Now is it clear? Now is it getting clear or not, Kevin? Yes? Okay, now it is clear. Still, I think because there are multiple parameters and there is a confusion that people might be getting in this case, just consider that in the case of the main idea that is happening in the case of softmax regression is for example, if your data is getting classified into n different classes, then your output hypothesis will contain n different values. Okay, n different values will be contained, and all these values will be between 0 and 1, and the summation of all these values will be equals to 1. If you see, your hypothesis function h of x in the case of softmax regression is e raised to zi upon summation of I is equals to 1 to c e raised to zi. That is, you are trying to normalize the value. That is what is happening. That's why the value will be between 0 and 1, and all the values, summation of all the values will be equals to 1. Yes or no? So this is clear. I hope that this is clear. So in the next lecture, maybe we'll discuss the loss function in the case of softmax regression, and then we'll end the discussion of our in the case of logistic regression, and we'll start with perceptron, which is the base of neural network. Perceptron. We'll do a small discussion on perceptron, and that will be end of our sectional syllabus for second session. Okay. So up to this, everyone is clear with today's discussion. So what you can do as a homework for today is, first of all, for those of you who didn't understand the gradient descent calculation for the case of logistic regression, you may try this at home, that you may try to derive the logistic regression gradient descent formula for the case of logistic regression with the hypothesis function h of x is equals to 1 plus e raised to minus z. That is what you have to try. And the second thing is, we'll further discuss on the softmax regression in the next lecture. But for now, also try to estimate. So we already discussed in the yesterday's lecture that convex and non-convex form. So we already discussed in the previous lecture. You can also try an experiment for MSE loss. Take MSE loss as your loss function, and hypothesis function is equals to 1 plus 1 e raised to minus z, and try to estimate whether the double derivative of your MSE loss function with respect to parameters is always greater than 0 for all values of theta, yes or no. For both the values, for take MSE loss and take binary cross entropy. Both of this, and take this hypothesis function in both the values and try to get when is your value greater than equals to 0 for all the parameters, right? So these two things you can try at home. By tomorrow, I'll upload the PPT so that by on Friday's lecture, we'll try to clear all the doubts that you have. So I hope that that is my idea is that by tomorrow, if I upload the PPT, so you study the PPT once, so that we can discuss on Friday whether you are having any doubt in any of the points that we have discussed so far. So everyone is clear with the idea what they have to do till Friday? Yes or no? Okay, I'll upload by today. I'll try to upload by today itself so that on Friday, I assume that you all have to study the PPT once so that we can clear all the doubts, whatever doubts or any problem you are facing in understanding any concept, we can discuss on Friday. Okay, so I'll upload it today itself so that we can perform the proper discussion on Friday. Okay, is everyone clear with the what we have to do? Yes or no? All right, so I'll be ending the meeting now. And you
ma'am, I have one announcement. Can I announce?
Yes, ma'am. Yes.
All of you, tomorrow's evaluation stands cancelled. Instead, it is preponed to today. Instead, yesterday it was announced that on Thursday we have evaluation of roll number 21 to 60, but instead now the schedule is 21 to 35. That is today 2:30. Remaining students from 35 onwards will be announced later. So tomorrow you don't have any evaluation. Instead, you have today. Are you clear with this? Roll number 21 to 35 is today. Are you clear with that? All of you, roll number 21 to 35. Are you there? Are you clear with it? Already it is announced in the classroom. Okay, great. So today we prepared, we present at the 2:30 to 3:30 timing in the regular meeting, and tomorrow you don't have any evaluation, right? And in case any, I will announce. But what was announced earlier is stands cancelled. Is it clear? Roll number 36 onwards, are you clear with this? Roll number 36 onwards, are you clear with this? Okay, that's good. That's good. Okay, fine. So other schedule will be announced in the classroom. And thank you, madam. I'm done with that. Thank you very much, madam.
Fine. So I'm ending the meeting now. So I'll upload the PPT and we'll further discuss on Friday. Fine. So now I am ending the meeting.